those two videos of the two mechanisms, two ways in which the reaction can happen, right?
Yeah.
And then at the moment we were leaving, I was saying, make sure you watch these again, right?
Yes.
So, let me just say this again. If you're not doing this work every day, it's not going to work out. Not going to work out. It's going to be very frustrating and disappointing for you, and of course for me as well. Are you telling me since Monday we didn't have 10 minutes to watch two videos? Not possible. Isn't that right, guys? Yes? So you got to decide how invested you are in this process, because if you're really invested, you got to do it. I wish I could just buy this box of magic pills and give one to each of you. It doesn't work that way. So think about it. Please understand, it's very easy for me to just go on. Just keep going on and on and on and on and assume that you got it. But that's a wrong assumption on my part. Also, please understand, how many of you are planning to transfer to a university next year? Whether it's UW or Western or Wazoo or something out of state, almost all of you, right? Even if you're not raising your hands. Do you know what's the size of this class at UW?
Triple.
Triple? No.
No.
It goes in hundreds. Do you really think that's a good learning environment for concepts such as these? No. So let's make use of this. You know me, I know you. We can work closely together and do the work that's needed so that when you go beyond, you know this stuff. But you gotta do the work. Yes, Eric?
Can I riff on that?
Yes, please.
So, I know a number of people who've gone through this class in the past and wandered off to biochemistry and other things, and they just go on about how great this class is.
Because I'm great, not just kidding. But the point is, Eric, right? It's the learning environment, right? We have 18 together plus me, 19. We can actually have those connections that you can't have there.
She just
Yeah.
got an email from Gabby.
Yeah, I mean, it's nice of him to say hi. It's always fun to hear back from students who are here. But the point I'm trying to make is, if you're not doing the work that you're needed to do at home, then you're not doing your part. And then I can try till I go crazy. It's not going to work. It's not going to be worth it for your time. May I just be harsh and say you're wasting your time. Period. And I do not believe that you guys didn't have time 10 minutes from Monday to today to watch those two videos. Can't believe it. So guys, that's your decision. Because of course, everybody here is an adult. So, let's try these.
Yeah.
Or pretending to be.
Okay.
Okay. Or, okay, maybe I said that wrong. Or expected to be in what your commitment is. Either way you look at it. Okay, so I'm writing a few equations here. We are talking about substitution only. Nucleophilic substitution is what we are referring to. Since my brain is still stuck there, we just barely started looking at mechanisms. We are going to learn so many different mechanisms, and if you don't really understand them, you can't do this. So let's not waste your time. Let's not waste my time. You've got to do your part. Okay. So, the question is, what I'm writing here is for you to complete each of these equations by either providing the product or missing substrate or missing nucleophile. Whatever might be missing, and we're only focusing on substitution here. So, maybe I'll do that later. Okay. So we are completing these equations, 1A, B, C, D, E, by writing whatever is missing. The main components of nucleophilic substitution reaction is a substrate which for us, for now, it's an alkyl halide is a substrate, which has the leaving group. Needs a nucleophile which takes the place of the leaving group and gives us the substitution product. So I have A, B, C, D, E, F, 6 equations here. And one of these 3 components is missing. Either the product is missing, or the substrate is missing, or the nucleophile is missing. You got to tell me what that would be for each of them. Please, go ahead, 5 minutes. We don't have more time. Maybe 10. Work with each other. Let's figure that out. Please, go ahead. Talk to each other. Yes, absolutely. As you're getting done, feel free to write on the board. Remember, the nucleophilic substitution reaction is the nucleophile, which is the electron-rich particle, attacks the electrophilic carbon and kicks out the leaving group and takes its place. That's the basic nucleophilic substitution reaction. Okay. Maybe can we just do a different color pen just so that it stands out? That's all. Okay. The substrate is what has the leaving group, and for now, just for now, our leaving group is halogen. For now, of course, that's not always the case, but for now, the leaving group is halogen. So that's why our substrate is an alkyl halide. Alkyl halide. The nucleophile has to be something that is electron rich. The nucleophile kicks out the leaving group to give us the substitution product. Which one?
Oh, no, I'm.
Oh, okay.
Yeah.
Okay. Don't get scared about that. My apologies. I wrote it all and then I realized, but she did it. So that's on. Was that you, Jasmine? Who wrote that? Yes. So your answer is correct. However, you need to write it better. So that new bond that you made, is it going to the hydrogen that it's bound to? To make sure that it's connecting the correct atoms.
Feels like it should be in
And where's the charge? So same thing. Which atom has the charge? Is it the hydrogen that has the charge? Or is it the oxygen that has the charge? So by drawing in that way, you're specifying the whole thing. There we go. No, no, good.
Oh, I skipped 5. You skipped 5. Yeah.
Does that make sense?
I counted 5. I went 1, 2, 3, 4, 5.
Okay, 2 more left, guys. Let's do this very quickly. 2 more left, please. So, the most electron-rich thing acts as the nucleophile, and it kicks out the leaving group, which for now is the halogen. Anybody? Anyone? 2 more left. E and F. Let's go draw it. Oh,
I was gonna draw
there you go, babe. Here you go. Yep. Cool. So, once again, the nucleophilic substitution reaction, although I'm going to, oh, fine. The nucleophilic substitution reaction is where the nucleophile is the electron-rich thing. Which of these is the electron-richest? Would you all agree that this is ionic?
yes.
And if it is ionic, which means it's a combination of cation and anion, right? So if you look at the 2 reactants in this example, this is the most electron-rich thing. That is your nucleophile. So it's actually nice to identify the nucleophile. And then here is the electrophile because it's attached to the leaving group. This is your leaving group, am I right?
Yes. Yes.
So the nucleophile replaces the leaving group, gives us the substitution product. Everybody okay? Yes? Everyone recognizes ET is ethyl?
Yes.
Okay, does anybody have questions on A? Cool, so same thing here in the next one. We have 2 reactants. Where is the highest electron density? That's our leaving group, which means this is our electrophilic carbon.
Yes.
Is that right?
Yeah.
So where is the nucleophile? That guy.
Methanol.
But is it ionic or molecular?
It's a molecular compound.
There are no cations or anions. Exactly, there are no cations or anions. What is the bonding? Which atom has the highest electron density in that case?
Oxygen.
Because, why? Because of the shape at oxygen. It's bent. Isn't that right?
Yes.
And it has lone pairs. And the bond polarity is in the direction of the oxygen. That means this is the highest electron density atom. Agreed?
Yeah.
But there are no anions because it's not ionic, it's molecular. Are you all with me?
Yep.
So, the negative attacks the electrophilic, kicks out the leaving group. Do you agree we would get this? Yes?
Yes.
Now what is that? In case you're wondering, what does that even look like? So again, let's think about this, guys. That what is that bond? The bond is between carbon and oxygen. That's it. But did we break any of those bonds just yet? We will do that later. But did we break any of these bonds just yet?
No.
So those bonds still exist. Which means the oxygen has to have a
Positive charge.
Because it's making 3 bonds. If you calculate its formal, thank you, is plus. Everybody okay? Please notice the difference. If it's ionic, well, you have a clear anion. But if it's molecular, then you're looking for the highest electron density atom in that molecule to do the attack. You guys with me, everybody?
Yeah.
Okay, so once again, I think in this case, I gave you the reactant and the product, right?
Yeah.
So you're thinking that, oh, that's the leaving group. What came in?
A hydroxide.
And if it is this okay?
No.
Because OH, well, that can't exist. OH what? Well, then it probably has a negative charge. Isn't that right?
Yes.
So then, if you, by the way, just wrote that, didn't write NaOH, if you just wrote this as hydroxide, is your answer correct?
Yes.
Yeah? Do I have to write NaOH or is OH minus okay?
OH minus is alright.
Why is OH minus all right? Why don't I have to write NaOH?
The spectator ion.
It's a spectator ion. Who cares? Otherwise, okay. We good, everybody?
Mm-hmm.
Okay, do you all agree water is the nucleophile in this case? Because notice the leaving group was replaced by this whole thing.
By an H2O, yes.
Perfect. Next one. I gave you the nucleophile and the product. So how did you come up with the substrate? Well, you notice that that's your nucleophile. That's ionic. Please, potassium is a metal. It's ionic. Agreed?
Yes.
So that's right here. So therefore, that means that the rest has to come from the substrate. And all he did was added a halide, iodide, bromide, chloride, whatever, IClBr, whichever halide as the leaving group. It doesn't have to be I. It could have been Br, it could have been Cl. Who cares, as long as you have a leaving group on that position. That's all that matters. We good, everybody?
Mm-hmm.
Next one, does that make sense as well?
Yes.
The only thing, and yes, it's correct, it's absolutely correct. But can we elaborate, what does that even mean?
There's
So-
2 hydrogen bonds at the end with a methyl group connected to it.
Exactly, so the nitrogen has 4 bonds. And that is the reason why it has a positive charge, absolutely. So this is just some examples of substitution reactions, nucleophilic substitution reactions. Please note, nucleophilic substitution reactions use a substrate that has a leaving group. Nucleophile attacks, kicks out the leaving group, takes its place to give us the product. So if I were writing a nucleophilic substitution reaction, I would say anything that has a leaving group, whatever the leaving, for now, our leaving groups are halides, but we will look at many examples where that is not the leaving group. But there's some leaving group reacts with a nucleophile that has to be electron rich. It is the nucleophile that attacks the electrophilic carbon, kicks out the nucleophile to give us the substitution product and the outcome. Make sense, everyone?
Yep.
So the last thing we did was, on Monday was, okay, here's a substitution reaction. There are 2 possible ways in which this can happen. There are 2 possible mechanisms in which, the way the reaction can go. Can someone remind me what were those 2 kinds of mechanisms for nucleophilic substitution called?
Concerted.
So the SN1 and SN2. One of them is concerted. By the way, what does the word concerted mean? One step.
Just one step.
Rate of bond breaking is the same as rate of bond making, so everything happens together. So which one is concerted? SN1 or SN2?
SN1.
SN2 is concerted in one step.
Okay, here's SN2.
Rate of bond making equals rate of bond breaking. Yes, just
I actually have a question about this. So, the example that we were shown on Monday, it was like the same reaction.
Yes.
And you showed it.
just
both
as
in
an
one.
example.
So, is there like certain ones
Yes.
that are like
Exactly,
similar?
exactly. And that's the detail that we are going to look at starting today. And that's why if you had watched the video, it would have really, really helped. But no, that's the detail we're getting into.
Okay.
Is this preferred or that preferred given your conditions? What's the substrate? What's the nucleophile? What's the solvent? And then you decide, okay, this prefers SN1 or this prefers SN2. Absolutely. So that's where we're headed, okay? Concerted means everything happens together. So if that's the case, is there an intermediate in a concerted mechanism?
No.
Which means there is no intermediate. Please make sure anytime, and this will happen a few times because a few mechanisms are concerted, meaning no intermediate, please make sure when you are writing those mechanisms, you show the transition state because there's no intermediate to show. So therefore, please make sure when you write the mechanism, you're showing the transition state. We'll do examples, so you'll know what does that mean in this example, in this case. So we'll do that. Okay, what's the other one called? SN1, right?
Yes, SN1.
Is this concerted or step
Multiple
steps? But typically 2 steps, right? For the substitution part, it is just a 2-step process. Isn't that right? And we will write those again when we look at examples. So does this have an intermediate?
Yes, it does.
What intermediate does it have?
Carbocation.
It always goes through, there's no free radical now, guys. That was only for that reaction. This reaction is completely different. This goes through a carbocation intermediate formation. And so on and so forth. I think this is where we stopped, kind of. And I kind of gave you an example just to bring it a little perspective. We good?
Yep.
Okay. We are going to start with SN2. We're going to look at all the details of SN2, look at examples of SN2, then go to look at SN1. So let's start with SN2. So SN2, what is its, what do these letters and numbers stand for? S is what?
Substitution.
M?
Substitution, nucleophilic,
And two?
bimolecular.
What does that mean? Bimolecular.
2 things are.
Exactly. So bimolecular basically means that the rate of this reaction equals the concentration of the substrate times the concentration of the nucleophile. Both the substrate and the nucleophile will affect the rate of an SN2 reaction. That's why bimolecular. 2 things are determining the rate of this reaction. We good? We're not doing any math, so don't worry. Let me give you an example. We'll write the mechanism. We'll get into the details of the mechanism as we go step by step by step. Okay. Can someone tell me what is the expected substitution product for this reaction?
Cyanide, or the hydrocarbon with the cyanide plus sodium bromide.
Good, but don't call it cyanide because cyanide, ide means it's an anion. You mean cyano,
Cyano group.
right?
Okay.
A nitrile basically, right?
Yes.
And of course the byproduct, in this case sodium bromide. Please don't be offended if I don't write the byproduct because who cares? We are interested in the organic product. Do you all agree?
Yep.
Now, if this reaction does go through SN2 mechanism, why? We'll get to that part. But because it goes through SN2 mechanism, and I'm telling you it does so, let's write its mechanism. Now, in SN2 reactions, by the way, what's the actual nucleophile in this reaction? CN, just CN?
CN
minus, cyanide. So CN minus is cyanide, but that's not CN minus, right? That's called a cyano group. This whole thing is called a nitrile compound, whichever way. Okay, so the nucleophile cyanide attacks the electrophile. There's a reason I'm showing my curved arrow the way I am, which we will discuss as we go, and breaks that bond. it's concerted. The rate of this is the same as rate of this. No intermediate. If there is no intermediate, we must show the transition state. So what does the transition state of this reaction look like? What's happening to the CC bond?
It's being made,
And what's happening to the CBR bond?
it's being broken.
Okay, but at the transition state, it's not completely made or completely broken, right? That's that's partially made and that's partially broken. Agreed? Everybody okay?
Yes.
The symbol for transition state is that. That's how we represent that this thing is a transition state. What am I missing here?
Charges.
Good. So let's process. This was a full negative.
Mhm.
As it's giving its electrons to the carbon, what's happening to the negative?
It's not as negative.
So what should it be now?
Partial negative.
Br was no charge, but it's moving away with those electrons.
So that's another partial negative.
Exactly. Isn't that right? Electrons. Can be partial positives. I heard someone say partial positive. Please think about this. If this were partial negative and this were partial positive, what's the sum?
0.
Is this neutral?
No.
No. If you look at this whole thing, it's 1 minus, so you have to keep your charges consistently balanced as well. Delta minus plus delta minus is minus. Isn't that right? Half minus plus half minus is a full minus. You got to keep your charges taken care of as well as you go through the steps. Everybody okay?
Mhm.
Again, one of the other ways to look at it is, this is giving electrons, so it's becoming less minus, but it's not 0 just yet. And this is taking electrons, so it's becoming minus, but it's not at a full minus level just yet. Now, once this has gone through, once this is left and that is come in, what's the product? You guys agree?
Yep.
Everybody okay? Yes. So please, that's how we write SN2 mechanisms. Because it's concerted, we must show the transition state. Are you guys with me so far?
Yep.
Everybody okay? Cool. Now let's discuss the details. By the way, what's the hybridization state? Let me just draw it again. Of the carbon where the leaving group is. What's the hybridization state of that carbon?
sp3 hybridization.
Good. If it's sp3 hybridized, how many hybrid orbitals does it have? 4,
It has
right?
4 hybrid orbitals.
Because it has 0 unhybridized p orbitals. So
It
if
has 4 electron groups.
if this carbon is sp3 hybridized, I'm going to try and draw it, and I know I'm not a very good drawer. So if you remember the shapes of the hybrid orbitals, here is one hybrid orbital which is connected to Br. Okay, here is another hybrid orbital which is, and it's got its minor lobe which is connected to the rest of it. Who cares? And then of course there are 2 other hybrid orbitals, right? Which is connected to hydrogen and hydrogen. Isn't that right?
Yep.
Now, which orbital is the nucleophile trying to grab when this reaction happens?
The one with the bromine?
So you think it's coming right here? How can it? Because bromine is occupying
Oh,
that space,
right.
right? Louder?
Unhybridized over?
There are no unhybridized.
Just share it for a second.
So is the nucleophile, when it's coming in, where is it going? Is it going here? Can't. There's bromine sitting there. Do you guys agree?
Yes. Bromine
Okay.
is already out.
Is it going here?
No, there's a
Hydrogen is
hydrogen
taking
there.
that spot. Can it go here?
No.
Can it go here?
No.
Where is it going? That's why I love that video, because it shows you. The nucleophile in SN2 is actually trying to grab and overlap the antibonding orbital of the same sp3 hybrid that has the leaving group. So if this is the sp3 hybridized orbital where the leaving group exists, the nucleophile is trying to come to that little tiny antibonding side that's opposite the leaving group. This is very, very important for SN2 reactions. SN2 reactions require that the nucleophile comes from the side opposite, 180 degrees. 180 degrees from the leaving group. Whichever side the leaving group sits in the molecule, the nucleophile needs to approach the anti-bonding orbital of the same orbital. So that means it has to come from the opposite side. Has to, doesn't have a choice. That is why notice, when I drew my curved arrows, notice how I showed it. Very intentionally, this was very intentional. When I was showing my curved arrow, I tried to make its approach be opposite where the leaving group is. Because this sp3 hybridized orbital, the nucleophile has to come and overlap with the antibonding side of the same hybrid orbital. We good? Forget about hybrid orbitals and all if you're not able to picture it, but remember, for SN2, the nucleophile must come from the opposite side, otherwise it's not SN2. We good, everybody?
Yep.
So, what if, therefore, this were the reaction and we are only focusing on SN2, just SN2 for now, not SN1. So, what if we had, let's say, can you tell me what's the name of this compound, and let's do it in 10 seconds. Because again, naming is something that we have to become. Hopefully we've done it enough that we don't have to think about it.
2-chlorobutane.
Say it again. Not quite. Not quite. Not at all.
R2-chloropentate?
You gotta give stereochemistry. If stereochemistry is shown, you've got to give it. Got to. Is it R? Carter said it's R. Is it R? Please let's confirm.
Clockwise.
Priority 1, priority 2, priority 3.
Clockwise is R.
Absolutely. So it's R2-chlorobutane.
It's chlorobutane.
Okay, let's say this R2-chlorobutane is reacting with what's the product? SN2. You're only thinking SN2 right now. So, I'm writing the mechanism to explain the product. If it's SN2, what should be the direction of approach of the nucleophile?
180 degrees opposite the chlorine.
And kick out. Isn't that right?
Yes.
Let's draw the transition state. That means this is partially broken, this is partially created. Am I right?
Yep.
Charges. Where are the charges? Actually, I did that wrong. Give me a second, please. Sorry, guys. Sorry. Can't do that. I meant to do this. Sorry about that. Charges. Where and what?
Partial negative on chlorine and partial negative on the first carbon of the alkyne.
And when it goes through, what's the product? Anyone? Where is the nucleophile attached? The same carbon?
Yes.
But what about its direction? Exactly. 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 You guys see that? So in SN2 reactions, the nucleophile always comes from the opposite side of the leaving group, which basically means that SN2 reactions will always always demonstrate inversion of stereochemistry. If that is R, what do you think this is?
S.
There will always be inversion of stereochemistry because the nucleophile must come from the opposite side of the leaving group, wherever the leaving group was. Are you all seeing that?
Yes.
And why does that have to happen? Because it's a concerted mechanism. There are no intermediates, so therefore that's the only way it can do so. You guys with me? Okay, let's try a couple more times. A question, Eric?
What's the name of that?
We don't know that
I
yet.
don't think so, okay.
We are about 3 chapters away from there.
Okay, so, but it would be, depending on how it goes through, it might not actually be S per se.
In this case it is, because that has to be
Okay.
priority 1, that has to be priority 2, priority 3, so yes.
Okay.
But I hear what you're saying. What if the nucleophile had a different priority than the leaving group? Then absolutely. So if you can remember that the nucleophile has to come from the opposite side of the leaving group, that's more important. Okay, let's try this a couple more times, please. Can you tell me the name of this guy?
Trans 1-bromo-4-methyl-cyclopentane.
Perfect. I heard trans, I heard bromo, I heard methyl, I heard cyclopentane. What was in between there?
Cycle?
What about the positions?
1-4.
Oh.
Actually, that was a mistake. I don't know, 1-3.
1-3.
Oh,
I don't know if you guys noticed there was a mistake in the quiz, which I fixed on the key. So please, when you look at the key, take note of that. 1-3. Assuming only SN2 right now. That's the only thing we are talking about right now. So please, now we have to be very specific in how you draw the product because SN2 is highly stereospecific. It's very specific in the stereochemistry of the product, so you got to take that into account if that is shown. Please go ahead. So what will be the product for the first reaction? Anybody? SN2 only.
Cis.
You can't name this group, we don't know that
Okay.
yet. But I think what you're trying to say is, let me know if
It's a cis compound.
Yeah.
right? What's the nucleophile though?
S.
Just S?
SCH3.
minus.
The minus is neutralized because if you attack it right there, kick out, right?
Do you want us to show these arrows?
No, because that's not the mechanism, that's an overall reaction. But I want to write a mechanism in just a couple more minutes. That was more of me saying, well, that's what's happening. Okay. Everybody get the same product?
Yes.
Everybody understands?
Yeah.
In SN2, the nucleophile comes from the face opposite the leaving group. If the leaving group is up, the nucleophile comes from down. If the leaving group is front, the nucleophile has to come from back, and so on and so forth. Yes?
So did the product matter if it was going up or?
Doesn't matter. Again, where is the leaving group? The nucleophile has to be in the opposite side. That's the important part. Now, should I change that also? Should I change this direction as well?
No.
No, the reaction didn't happen there. So no change there.
It wasn't touched.
The reaction is on this carbon right here, so that's where the inversion of stereochemistry happened. You guys seen that?
Yes.
Okay, what about the product for the next one?
It'd be SNS.
So should we change
No.
this stereo center?
No.
No, that's not where the reaction happened, absolutely. And what happens to that stereo center?
Up
That's the one
front.
that gets inverted. And what's the nucleophile? It's an alpha. Absolutely. You guys okay?
Yes.
Now we need to practice writing these mechanisms. If it's SN2, your mechanism, your transition state has to be clear, where it shows the two things are opposite each other. I was trying to do it right there also. I don't know if you noticed it or not, but let's try it another time to make sure we see that, yep, it's the nucleophile is opposite the leaving group. So if you're writing the mechanism for the first reaction that is shown on the board, and SCH3 negative, that's your nucleophile. Sodium ion is just a spectator ion. Now we need curved arrows because you're writing the mechanism, we need curved arrows. This comes from the opposite side, kicks out the leaving group. So therefore the transition state has to be very clear. The direction of this bond being broken is up, but the direction of the bond being formed is opposite. So when you write mechanisms for SN2 reactions and you show the transition state, you got to show that spatial perspective.
Did you forget the partial charges?
I was getting to that, so go ahead, tell me. Go ahead.
Both are partial negative?
Both are partial negative again in this case again. And then of course when it goes through you get the product. Everybody okay with that? So please practice drawing these. These do need practice.
So this is like, you don't have the arrows there because that's the product, and over
That's
here is
the
the
overall
mechanism.
reaction.
And this is
the
a mechanism. Okay.
Exactly. That's the overall reaction. This is the mechanism. Do write the products, guys. I'm lazy. I wrote them there, so I don't want to write it again, but you should write the product. That's where it ends up. Everybody okay?
Yeah.
Nope.
Oh, sorry.
Not
Yes,
for-
sorry. Okay, let me show you. Remember, I was saying this earlier, that for now, our leaving groups are halides.
Yeah.
But leaving groups are not always halides. They can be anything, and we'll talk about what's a good leaving group, what's not a good leaving group, how do we decide that. We'll talk about all of that as we go one step at a time. But I want to show you another reaction where the leaving group is not a halide, such as now this is, if this were undergoing substitution reaction, what would have to be the leaving group?
The
Right?
hydroxide?
And what would the leaving group, well, it's OH right now, hydroxyl right now, but what will it leave as? Become hydroxide and leave, right? Please understand the difference in our vocabulary. This is not hydroxide. Why is this
Hydroxyl.
not hydroxide? Because it's not an anion. That's a covalent bond. It's polar, but it's
It's
covalent.
attached to the hydrocarbons.
So you can call it a hydroxyl group or an alcohol group or any such thing. But when it does leave, when it does get kicked out by the nucleophile, what does it become? Just this guy. What does it become?
And a hydroxide ion?
That is hydroxide. So they're different things. Again, our vocabulary is telling us what we want to say. Are we okay? Okay, coming back though. So as an example of a reaction, if this were to react with, we saw this in chapter 10. One of the ways to make alkyl halides is react alcohols with HX. Do you remember that?
Yep.
And it therefore becomes, in this example, can someone tell me what will be the byproduct of this reaction?
Water.
H2O. Do you guys remember that general reaction? Alcohols with HX become RX, ROH with HX become RX. So here's an example. Now, do you guys agree it's a substitution reaction?
Yes.
Right? So, assuming it's SN2, we're only talking about SN2. Let's write a mechanism. Now, the problem is, this is a very bad leaving group. It's not a good leaving group. Why? We'll get there. We're not there yet. Believe me, for now. Just take my word. It's a bad leaving group. It doesn't want to leave. Not the way it is. So, we have to do something to first make it a good leaving group and then do substitution reaction. So you have to write a mechanism. We're not adding anything else to this reaction. It is this reaction. But when the mechanism happens, you got to write it in such a way that first that guy needs to become a good leaving group and then substitution happens. One of the ways in which alcohols can be made into good leaving groups is by protonating them, putting a proton on them. With me? That's one of the ways of doing so. And by the way, we look at this quite a few times. So let's try and understand, and we look at the details as we go, one step at a time. So the first thing the mechanism has to do is convert that, this is a bad leaving group, we need to convert it into a good leaving group. And one of the ways to do so for alcohols is to protonate it. What does that mean?
Add a H plus on it.
And who's going to give an H plus?
HBO.
Why? Because it is an
Acid.
acid. Acids give protons. Who takes the proton? If this is the one that's taking the proton, what is that guy behaving as?
A base.
A base. So the first step in the mechanism is not substitution in this example. The first step in the mechanism is actually an acid-base reaction where this reacts as a base with HBr, which reacts as an acid. An acid donates a proton, the base takes the proton. We've seen this reaction, by the way, last quarter, where that takes a proton and gets protonated. Please, can you tell me what will be the outcome of that step?
The alcohol, the hydrocarbon with an H2O group on it plus Br minus.
So,
H2O plus Br minus.
Do you guys agree?
Yes.
Is this substitution?
No.
No. It's simply an acid-base reaction where one gave a proton, the other took a proton, that's it. But we have to do so because by doing so, a bad leaving group actually becomes a good leaving group. That's a very good leaving group. What's the property of a bad leaving group? What's the property of a good leaving group? We'll get to that part, but just please notice. So step one is this. Now that we have a good leaving group, that's when SN2 starts. That's when this is the SN2 part of it, which is of course concerted. Everything happens at the same time. So the protonated alcohol is the substrate. That's our leaving group. What's the nucleophile?
Bromine.
Mm-mm.
Oh, not bromine.
Is it bromine?
Hydrobromic acid.
No.
Oh, wait.
Bromide.
Bromide.
Bromine is an atom with 7 electrons. That's bromide with 8 electrons. Again, vocabulary. Bromide acts as the nucleophile. It is going through SN2, which means the nucleophile has to come from the opposite side of the leaving group. Let's try and draw the transition state. What would the transition state of that SN2 look like? Once again, you got to be very clear in your drawing. This bond is starting to break. That bond is starting to form. Opposite sides of each other. Do you guys agree?
Yep.
Of course, I did not put the charges because I want you to tell me what charges where.
OH2 has a partial plus.
Why is it partial plus? Why isn't it partial minus as we saw in previous examples?
Because it was plus to begin with and it's gaining some electrons.
Exactly. So you gotta process it, guys. It was plus before and it's getting electrons. So the plus becomes less plus. Isn't that right?
Yes.
And what about BR? It was minus before and it's giving electrons. So what does it become?
Partial minus.
So, we good, everybody? And when that goes through, what is the product? Everybody agrees? If I were drawing an energy diagram for this mechanism, there are two steps here. Except SN2 is just a single step. SN2 is concerted. But we had to add another step to the mechanism so that the bad leaving group can be made a good leaving group. So if you're drawing the energy diagram, you will see two curves. There is an intermediate in this case. If you think about it, that's an intermediate. But please understand, SN2 is just the second step. The first step was just an attempt, just for us to bring it so it can do SN2 reaction. The SN2 is simply this part in this example. That's SN2, single step, transition state, product. This step was needed so that the bad leaving group could be made into a good leaving group. You guys okay? Yes, Carrie.
As far as drawing it, with,
Yes.
So the BR is facing like up now instead of down.
Yeah.
Is that like required? Is there a preference?
It's okay. Let's be honest. Okay, so in this particular example, is that a stereo center?
No.
Is that a stereo center?
No.
So it doesn't really matter, right? If there's no stereo center, it doesn't really matter. I just wrote it just to establish or demonstrate the fact that the nucleophile is coming from the side opposite to the leaving group.
Just emphasizing that it.
Exactly, exactly. But if it were a stereo center, then you have to be absolutely sure that you do so.
But it would be okay to write it like the first one with the Roman.
Depending on what you started with. Absolutely, yeah, exactly. Does that answer your question, right? Is everybody okay there? Everyone? Do we all understand this idea of inversion or stereochemistry?
Yes.
Does everyone understand why are we protonating the alcohol, at least for that example? Because we're going to see similar examples as we go forward. Do we all understand that? Okay, cool. So let's start with another SN2 reaction example, and then we'll look at factors that affect SN2 reaction mechanism. Factors that affect rate of SN2. In which cases will SN2 be favored? Which cases SN2 will not be favored? In which case will SN2 go faster or slower, as the case might be? So there are some very distinctive factors we can look at to decide those things.
Quick question.
Yes, please.
Is there any general, how do you identify SN2 versus SN1?
Perfect question, just not there yet.
Okay.
So here's my plan, just so that everybody knows. We are going to detail study SN2, then we will detail study SN1, then compare the two. Then we will look at elimination E1, E2 individually, and then compare all four and decide how to make a prediction. Here's the reaction, should it be SN1 or SN2 or E1 or E2? Because there are really four mechanisms that are competing at the same time. So that's my plan. Is that okay? Because we don't even know what SN1 is, so how are we supposed to even bring it into the discussion yet? My goal is hopefully by Monday we'll be there. But let's first look at what factors favor SN2 mechanism over SN1. So the first thing we always look at, guys, when we are trying to make this determination, the first factor we look at is the substrate. Remember, substrate is the one that has the leaving group. Whatever the leaving group is, that's the one we look at first, is the substrate. You guys with me so far?
Yeah.
Okay, let me draw some examples, then I'll ask you questions. let's say we are comparing SN2, just focusing on SN2, that's it. We are looking at methyl bromide. So is that what's the hybridization state of that carbon?
sp3.
So we have Br, we have H, H, and H. Isn't that right? Let's compare that to bromoethane. Yeah. Where is the electrophilic carbon? That one? What's the hybridization state of that carbon? Sp. Did I hear sp3?
sp.
I know I heard it wrong. Agreed?
Agree.
Also sp3. We good, everybody? Now, remember in SN2, where does a nucleophile have to come from?
Opposite the
Leaving group.
the leaving group.
So think about sp3 and feel free to pick up a model kit if you want to make one model and then take a look at it. If you want to do that, feel free to do that. But the nucleophile has to come from the opposite side. Isn't that right?
Yep.
And remember, it's all in one step. This is still attached while the nucleophile is coming in. So, what things are blocking, in this example, the approach of the nucleophile as it approaches the carbon? What's coming in the way, so to speak, of the nucleophile as it comes?
The hydrogen opposite.
Isn't that right? Agreed?
But they're splayed out, right?
109.5 degrees.
Yeah, so,
Exactly. It's tetrahedral. So, yeah, but they're still there, right? Think of an inverted umbrella. If you really, an sp3 hybridized atom spatially looks like an inverted umbrella. You know, when the wind blows and it inverts your umbrella. So this is the handle of the umbrella and it's blown the other side by the wind. That's kind of what sp3 tetrahedral atom looks like. So you've got these things float and then the nucleophile has to come in. Agreed? Can you guys picture that? That's why the video. Please watch it tonight. It will really help in my opinion. So please watch it. It gives you the perspective. Okay, the same thing needs to happen here as well. The nucleophile has to still come there. What is coming in the way of the approach of the nucleophile in this example?
H,
H, H, and
C,
Methyl.
H3.
we good? In which of these two cases will the nucleophile have greater difficulty
Second one.
to approach there?
Second one.
Why?
Because
Because of the
more.
Because of this guy, because it's basically, again, they are all sp3 hybridized, so they're, do you guys agree? This is called steric hindrance. Sterics, we say sterics or steric hindrance or steric interaction or whatever term. The word steric is basically hinting to hindrance caused by crowdedness. If there's greater crowding, then something has trouble getting there. You guys with me? So, if this is going to have greater steric hindrance for the nucleophile to approach the electrophilic carbon compared to this guy, who will react faster with SN2?
The first one.
Do you all agree?
CH3Br.
Everybody
Yeah.
agrees?
Yes.
So if you understand this, can you compare bromoethane to bromopropane? Who's going to react by SN2 faster?
Ethyl bromide.
Do you all agree? Because again, if you think about it, that carbon right here, which is sp3 hybridized, but what is it connected to? It's connected to one hydrogen and two of those.
Two methyls.
So the approach of the nucleophile to that electrophilic carbon is even more hindered. You guys agree? So that's going to react even slower. SN2 only, we are only talking about SN2. And what about T-butyl bromide? Way slower. In fact, do you all understand that? So, when we look at substrate, because of the sterics to the approach of the nucleophile, the methyl substrate reacts fastest because there's barely any sterics. Hydrogens are tiny, they don't really offer much crowding. Primary comes after, secondary slower than primary. Tertiary is so slow that it cannot do SN2. Tertiary is so crowded that the nucleophile can't reach there. Can't. Primary is happy to do SN2. Secondary can also do SN2, although slower than primary. Tertiary can't do SN2. Are you guys with me? Does everybody understand? Okay, cool. Then please tell me. Here are some examples. Pick. Question? Let's arrange these in increasing order of SN2. Okay, so our goal is to arrange the structures shown in increasing order of SN2 reactivity, rate of SN2 reaction. So will you start with slowest to fastest or fastest to slowest?
Slowest to fastest.
Cool. So tell me what's one.
Wouldn't it, oh, one.
Did you say second one?
Yeah, the middle one.
The tertiary?
Yes.
Slower, oops, sorry.
Yes.
Slowest? That's two.
Yep.
Okay. Two?
The one on the right?
Secondary.
Because it's secondary. Okay. Three?
The first one says it's primary.
Yes.
Perfect. I'm getting my secondary to those symbols mixed up with. Right? Good? It's all about sterics. It's all about how crowded is that carbon where the nucleophile needs to go. The more crowded it is, the slower SN2 would be. Does everybody agree? Okay. What about the next set?
The
first one.
Is the slowest because it's tertiary? Good?
Yep.
Then it'll be the, third one.
Yeah.
Third one, because it is,
It's closer to the methyl.
and it
Yeah,
is
Secondary.
Secondary.
and it's closer. That's actually what I was trying to get to with these two examples, that these are both secondaries. Do you guys agree?
Yes.
But yet they have a different rate of reaction of SN2 because, as Carter said, this one secondary is closer to the methyl, so it's going to have slightly more crowdedness at that carbon compared to this one because it's farther away. Yes?
So if you were to put the bromine, on the left side like that,
Isn't that the same?
no,
Oh,
sorry, I mean for the
this
second
one?
one, for the, yeah, for that
Isn't
one.
that the same?
Yeah, I was gonna ask, would that be the
Symmetrical.
same?
It's
Okay.
the same. If it weren't symmetrical, then yes, that's a different story. But yeah. Okay, then what's 3?
So, second one.
No, there are 2 then.
3 is the fourth one.
And
4th is the second one.
agree? Everybody? So substrate is the first thing we look at. The more crowding there is around the electrophilic carbon, the slower is the SN2 reaction. Any questions about that? Okay, so the next factor we look at after, let's say the substrate is the same. So then the next thing we look at is the nucleophile. The nucleophile also affects the rate of substitution SN2 reaction because it's bimolecular, right? The substrate affects the rate of SN2, nucleophile affects the rate of SN2, so we should consider it. There are 2 things when it comes to nucleophiles that we look at. One thing that we look at when it comes to nucleophiles is its nucleophilicity. Nucleophilicity has to do with the fact as to how dense the electron rich center is, how high is the electron concentration on that atom. The more electron rich something is, the more nucleophilic it is because it has higher tendency to go and attack the electrophilic position. So when we say nucleophilicity, we are really talking about the extent of electron density. The more electron density an atom has, the more nucleophilic it is. You guys with me? Now in this context, there are again 2 factors that come in depending on what is being compared. So in this context, the first thing we look at is if the atom, hold on, actually no. I'm processing, give me a second. Well, yeah, 2, okay. First thing we look at is basicity. The more basic something is, the more nucleophilic it is, or the better nucleophile it is. The stronger nucleophile it is. Higher basicity, higher nucleophilicity. Let me give you some examples of that, then we look at the second factor as well. So for example, if you're comparing the nucleophilicity, which of these will react faster as a nucleophile for SN2 reaction, hydroxide or water?
Hydroxide.
Why?
Because
Absolutely. Actually has a negative charge. There's no negative charge there. They have electrons, lone pairs, but it actually, it actually has a negative charge. Agreed?
Yep.
How about, let's say A, B. Which of these 3 would you expect to be the strongest nucleophile?
The middle one.
Because,
It has a negative charge.
do you guys agree?
Yep.
Strongest nucleophile. Which of these would you expect to be the weakest nucleophile because it does not have as much basicity or as much electron density? Absolutely,
Right.
because it has a positive charge. You guys see that? This is the least nucleophilic. It actually can't. It's so less nucleophilic, it can't do nucleophilic substitution. Everybody agrees?
Yep.
So here's another example. Which of these two will be the stronger nucleophile? So you're looking at the basicity. If you go back to last quarter, how do we check which of these two is the stronger base?
Electron density.
Oh, oxygen,
There's a, say again?
Which one's more?
more electron.
Okay. Isn't there a better way of comparing base strengths?
Is it conjugate acid?
You have to look at its conjugate acid. What's the conjugate acid of HO minus?
H2O.
And what is the conjugate acid of H2N minus?
NH3.
Ammonia. What is the pKa of, I think the pKa of water is around 15.7.
Yeah,
And
15.7.
this is about 38 pKa. Which of these is the weaker acid?
NH3.
So then which of these is the stronger base?
NH3. Or NH2
H2N.
minus. NH2
You
minus.
guys agree?
Yeah.
So please remember, of course you're looking at electron density to compare base strengths with, but the correct way of doing that is to look at the acid strength of the conjugate acid. And remember, weak acid comes from a strong base, a strong acid comes from a weak base. Good. Okay, so what about these two?
What was the second one?
Say again. Actually, sorry, could I take this away for now?
Yes.
I do want to bring it, but not in this group. Sorry, it will come back. It will come back. So first thing we look at is basicity. Basicity basically tells us stronger acid. Now this factor is compared for atoms in the same period. Like oxygen and nitrogen, or carbon and oxygen, or whatever the case might be, they are in the same period. On the other hand, which is why I erased that, another factor we should look at is polarizability. Polarizability. And this has to do with the size of the atom. And here, the bigger the atom, more nucleophilic. So this is actually opposite basicity. Polarizability has to do with how much is the electron density spread. Because if it's spread more, it can reach that anti-bonding orbital, that's tiny space, more easily. So this is opposite of basicity. So for example, the one I erased earlier, if you're looking at OH minus and HS minus, this time you're comparing oxygen to sulfur. And these are in the same group. So which of them is bigger?
HS.
So this is important when you're comparing atoms in the same group, not period. So the bigger atom is more nucleophilic. It is able to carry our SN2 faster than the smaller one. Yes?
Can you repeat what you said about the electron density spreading?
So if you're comparing a smaller atom to a bigger atom, everything else being constant, the number of electrons being, valence electrons, I'm not talking about the core electrons, the valence electrons being the same and charge being the same, everything else being the same. So if you're comparing a smaller atom to a bigger atom, and have, for example, here, the number of electrons, valence electrons is the same for oxygen, for sulfur, and all that stuff. For which of these will it be easier to distort the electron cloud and reach, remember the goal is to reach this anti-bonding orbital.
Bigger one because it's more malleable.
That's why. And that's nucleophilicity. The nucleophile job is to reach here. So if it's bigger, the electrons are more in flux. They can move more. The electron cloud can distort a little bit and kind of reach that area much more easily than this guy can.
So it can it's flexible and it'll just fit.
Exactly. And then therefore it can grab that anti-bonding orbital, make the bond, kick out the leaving group, reaction has happened. So when it comes to it's a weaker base. It's absolutely a weaker base for the same reason actually, but meaning its ability to take a proton is lower than its ability to take a proton. But it's a much better nucleophile compared to that. You guys with me? Yes? So when you're comparing nucleophilicity, you have to think about, am I comparing atoms in the same period? Which is when you just look at electron density. But if you're comparing atoms in the same group, then you're looking at size. Bigger size, more nucleophilic. Are you guys with me so far?
And polar.
Everything else being the same, right? You can't, it's not a good idea to change more than one factor at the same time, because then it's hard to say, is this more important or is that more important, right? So everything else being constant, if you're comparing atoms that are in the same family, then bigger is a better nucleophile. Good? Okay, so which is a better nucleophile in that case? Is Cl minus or I minus? Better nucleophile. So once again, chlorine and iodine in the same family, same group. And then
Iodine.
it's way more polarizable. The electron density is so, it has the flexibility, it has the ability to, what's the word? Mold itself. Because it's far away from the nucleus, it can actually mold itself, it can move around and reach that anti-bonding orbital way more easily. Are you guys with me? Now this is not called sterics, by the way, because this is not interaction of atoms that are bumping into each other. This is more about the electron cloud being able to reach that area. Are you guys okay so far? But that's just factor one, nucleophilicity. You're looking at, okay, how nucleophilic is this thing compared to something else, in which case we are either comparing basicity or we are comparing polarizability, but there is one other factor that should be considered when it comes to the nucleophile affecting the rate of SN2 reaction, and I'm going to call it B. And that is the steric of the nucleophile. Sterics is about atoms bumping into each other. So, which do you think will be more nucleophilic? In which direction would the nucleophilicity go up?
Left to right.
Go up, left to right, or go down, left to right? For which of these will it be easier to reach that electrophilic carbon from the side opposite the leaving group? Exactly. T-butyl group, by the way, keep it in mind always, T-butyl group is highly bulky, very bulky, no matter where it is. T-butyl group is highly bulky. So absolutely, overall this being smaller, it can reach compared to the others. That's called sterics. You guys with me?
Yep.
Everybody okay? Sure? So if that's the case, if we understand this, let me write a couple of things, then I'll ask you the question. By the way, I do have a worksheet also for us to try and work on, but not there yet.
anti-bonding side, right?
Yes, anti-bonding lobe of the orbital. Orbitals have lobes, right? S orbital is just spherical. P orbitals have those two lobes. sp3 and sp2 and sp hybridized orbitals kind of have these two lobes. That's your bonding lobe. This is your anti-bonding lobe. Coming back. Please write the products. Let's do it quickly. Product. Very quickly. Done? Products? Everybody okay with that? I don't have to write it, right? Next question, which of these reactions will go faster? So notice the substrate is the same, right? So we are comparing the nucleophile.
Won't SH go faster?
Are you asking me, telling me?
Uh,
NAS will be faster because
NASH, okay, faster.
So you are you're looking at substrate first. If the substrate is the same, then you're looking at the nucleophile. Do you guys all agree?
Yep.
So same question, I'm going to write a couple more pairs here. Same question, and guys, for practice, because practice is all what's needed from now on. Complete it, write the products, write a mechanism, because the more times you do it, the better you will get at it. Which will go faster? Let me just write a few. I'm not writing the products, I'm leaving those for you guys to finish, complete, practice, write mechanisms. SN2 is what we are focusing on right now. So keep writing, keep writing. Here are a couple more examples. So can you tell me which reaction from the top half of the board will go faster? SN2, we are only comparing SN2s. I forgot what I wrote. Why? So first thing we look at is the substrate. Do you guys agree that for SN2, that's more crowded compared to that? Agree?
Yep.
Okay. What about these two? Which will go faster? So the substrate is the same. So now we're looking at the nucleophile. The second one again? What is that? It's not always the second one. I think that's how my brain is working right now. But what is the reason? This is bulkier compared to that. We good, everybody? Yes? Questions? Okay. So that's factor number 2. Factor number 3, when it comes to rates of SN2 reactions, is the leaving group. If you think about the mechanism of SN2, substrate plays a role, nucleophile plays a role, the leaving group also plays a role. Only if the nucleophile leaves can only if the leaving group leaves can the nucleophile come in. Isn't that right?
Yep.
Mm-hmm.
So we need a good leaving group. As you saw in the case of an alcohol, it's a bad leaving group, so we had to first make it a good leaving group and then do substitution. So let's understand what makes a leaving group a good or a bad leaving group. The basic idea is a bad leaving group is a good or rather strong base. Because if it's a strong base, it can be a good nucleophile. What leaving group does is opposite of what the nucleophile does. So they have to have opposite characteristics. The bottom line is that a good leaving group is a poor base. So when we saw earlier, remember the example of the alcohol?
Mhm.
So if this were to leave, what will it become? Anybody? You know, the nucleophile comes in, whatever the nucleophile is, and kicks this out, what does it become?
Hydroxide, OH minus.
But then if this leaves, what does it become?
H2O.
Exactly, right? Nucleophile comes in, attacks, kicks this out, what does that become? It becomes H2O. Which of these two is a stronger base? So then that is a poorer. And this is a weak base. So this is a, yeah, better, good, better because we're comparing the two, but yeah. So exactly, a leaving group wants to leave. So it needs to be a weak base when it's left, because if it's a weak base, then it's a weak nucleophile. It can't come right back in and kick out the other. You guys with me? So let's give you, let me give you a few examples of this. So, which of these, and I'll try to not have the second one be the right answer every single time. Faster SN2 is the question. With the nucleophile, whatever the nucleophile is, that's not our focus right now. Which of these will react through SN2 faster? So look at the leaving group. See what it becomes. Compare their basicities and then decide. Okay. We are now thinking about the leaving group. So if the nucleophile attacks whatever that is, sorry, wrong side. Sorry. And kick out the leaving group, what does it become? The leaving group, what does that become? On the other hand, if this kicks out the leaving group, what does that become? Anybody? What does that become? Sorry, could you say that again? Not really. Don't add anything. There's no H that we added here. So what does it become? If you just follow the curved arrows, doesn't it become that?
Yes.
What does this guy become? Isn't that right?
Yep. Both
Which of
have.
those is the weaker base? Which of these is the weaker base?
Second one.
This is taking us to first quarter. Which of those is a weaker base? Anybody? First I heard. Why is the first the weaker base compared to the second? Okay, and what is the structural thing you see which makes this a weaker base?
If you add a proton to it, it becomes a
I
carboxylic
think that's
acid.
something that was already said. Let's say something different. Why is this a weaker base?
A lily. Okay.
I'll take
Resonance,
that.
Resonance, yeah.
Good.
Resonance.
Just because that's not carbon, but
Yeah,
exactly.
it's not a carbon.
Exactly. I mean, can't we just delocalize that negative charge? And remember, resonance structures don't exist. What exists is the,
Hybrid.
and in the hybrid, where is this negative charge? Is it on the oxygen? It's actually delocalized over the whole system.
Mhm.
Here it's localized. The negative charge is only on that oxygen. Isn't
There's-
that right?
Yes,
That's localized.
there are single bonds.
So therefore, that's the weaker base. So if it's a weaker base, which of these two is the better leaving group?
First one.
And therefore, this reaction will go faster compared to the other one. Do you guys agree? Okay, how about this set? Same idea. So what does Cl become when it's left?
Chloride.
Cl minus, yes, chloride, and I becomes,
Iodide.
so which of these is the weaker base? Cl minus or I minus? Base, not nucleophile, base. Which one of these will react with H plus slow? Louder? And why is that? It's bigger.
Mhm.
Exactly. If it's a weaker base, this is a better leaving. Absolutely. That means this reaction will go faster. Everything else being the same. Make sense?
Mhm.
Can you pick the faster one here? Which reaction will go through SN2 faster? Sorry? The top one? Because that becomes OCH3 negative.
Mhm.
What does that become?
F.
If it were to be kicked out, it can't be because it's such a bad leaving group, you can never do it. It would become, right?
Ethane. Yep.
Not ethane,
F.
the negative, right?
Yep.
Which of these is a weaker base? Absolutely. Weaker base, better leaving group. So leaving groups also make an impact on the rate of SN2 reactions because unless the leaving group can leave, the nucleophile cannot come in. So a better leaving group is a poor base. A weak base is a good leaving group. Sounds okay, everybody? That is why when we were looking at the reaction of alcohols and we were trying to make it undergo SN2 reaction, we have to first convert it into a good leaving group. Only then can the nucleophile kick it out. Questions? Okay. The last thing we look at. First we look at substrate, then we look at nucleophile. The last thing we look, then the leaving group. And the fourth factor that can affect how fast or slow SN2 reaction goes is the solvent. All of these reactions are done and dissolved in a solvent. They're done in solutions. They're not done in pure form. So the solvent is the last factor that is considered for SN2 and SN1. Now please understand one thing, this is important. Solvent cannot make SN2 become SN1 or vice versa. Solvent just can make an SN2 be a faster SN2 or a slower SN2. Does that make sense, everybody?
Mhm.
Solvent doesn't change the mechanism. It just makes that same mechanism either go good at good rate or go slow. That's all it does. There are two categories of solvents. One category you already know. Please tell me if you do or do not. Polar or non-polar solvents. Is there anybody here who does not know what these are? We good, all of us? The other category of solvents, which you kind of heard a few days, maybe last week sometime, is protic or aprotic solvent. Can someone tell me what is a protic solvent or what is an aprotic solvent?
A
Anyone?
Protic solvent is something that can give or give away or get protons.
Not get, give only.
Okay.
Only give. Meaning it has ability to act as an acid if needed. If there were a strong enough base, it can act as an acid. Aprotic means it cannot give a proton. Isn't that right?
Mm-hmm.
Can you tell me in what kind of bonds? I didn't say that quite right. Can you tell me which kind of bonds are able to produce protons, H+? What kind of bond is able to allow us an H+? Louder?
And
Somebody said something.
OH,
Anion?
An OH or
anion,
not
not
what
anion.
anion? No. Whatever this is.
Okay.
An OH bond is polar, right? I thought I heard someone say polar over there. An OH bond is polar, isn't that right?
Mm-hmm.
In which direction?
Towards the
So
oxygen.
what is the electronic characteristic of the hydrogen? If this is delta minus, what is H?
Delta plus.
Isn't that close to a proton?
Yes.
Proton is H plus. So anything that has H with a delta plus, meaning a polar bond to a hydrogen, is capable of giving us a proton. Those are protic solvents. So absolutely right. And anything that has an OH bond, water, alcohols, carboxylic acids, those are all protic because they have a capacity to give a proton because of this bond. Is there another bond that can also do so?
NH.
Those are the two most polar bonds in Chem. I'm not counting FH because that's not organic. NH and OH bonds are the most polar bonds in organics. So if any solvent has one of these two, it can give a proton. Which kind of bonds are non-polar? The other end of the extreme. When you, exactly, CH or so on and so forth, when you have no OH or NH bonds, those are aprotic. I'm going to write a few solvents which you have to know. You just have to know, guys. Aprotic, polar aprotic solvents. Polar, they have to be polar because these are all ionic mechanisms. There are two electron processes, there's positive, negatives. So we do need polarity to dissolve everything. But those also have to be aprotic solvents. Favor SN2. Now the book I think does describe why. I'm not getting into the why part. Polar aprotic solvents make SN2s go better than polar protic solvents. It doesn't mean that the polar solvent, protic solvent, there's zero SN2. It just means that it'll go slower, that's all. I'm going to write a few of these on the board, which you have to always remember. You have to know those. So the commonest polar aprotic solvents that you must remember are the following. Let's start with something that you already know, and that is acetone. Of course, it's very volatile, so you really can't heat it too much because it will evaporate, but it is polar and it is aprotic. Everybody knows the structure? Everyone knows the structure?
CH3, COCH3.
Then the next few, okay, let's start with acetonitrile. I'll draw the structures as well as we go on. Then we have DMF, which stands for dimethylformamide. I'll draw the structure. We have DMSO, which stands for dimethyl sulfoxide, and I don't know, HMPA, This stands for hexamethyl phosphoramide. I feel like I'm forgetting one. I think that should be, because those may not be necessary. Okay, acetone structure everybody knows, so I'm not going. Acetonitrile is basically CH3CN. It's nitrile formed from acetic acid. DMF, dimethyl formamide, is an amide of formic acid, but with two methyl groups on it. Okay. DMSO, dimethyl sulfoxide, is that sulfoxide with two methyls. Again, please notice they're polar. Each one of them is polar, but aprotic because there's no hydrogen and oxygen and nitrogen. HMPA, phosphoramide, so hexamethyl. Give me a second, okay? Give me a second. So it has to be N, and then CH3, and they're pretty bulky also, with the exception of acetone and acetonitrile, they are pretty bulky as well. So you need to know these solvents. These are solvents. Their job is just to keep everything dissolved and homogeneous so that the reactions can happen. SN2 reaction is favored by using one of these solvents. With me? Everybody? Yes, please.
Between the four of them,
Yes.
is there like a ranking of which ones are better?
Not quite. I mean, I personally have never used HMPN, but it's there. I have most of the times used DMF and DMSO I've used. Acetone is extremely volatile, so it makes your choices very limited, right? You can't go above a certain temperature because it'll evaporate. So, is one better than the other? I don't think so. Some may be more common than the other just because they are more convenient to use.
Okay.
And DMF is definitely one of those that you might see more often. DMSO you might also see sometimes. HMPA probably not too much, but it's there. Are we all okay? So just to summarize the four factors that we have studied for SN2 reactions, please remember SN2 reactions are bimolecular, which means that both the substrate and the nucleophile will have a say in how fast or slow they go. So SN2 reactions, just to summarize what we've learned, number one, first thing is substrate. So this is all about sterics. The more crowded the electrophilic carbon is, the slower the reaction would go. So in general, methyl is fastest, primary, secondary, but tertiary never do SN2. They don't do SN2. Then we looked at nucleophile. And the idea here is that a good nucleophile or a strong nucleophile, and we talked about the different ways in which we can assess the nucleophilicity of a nucleophile, will make SN2 go faster compared to a weaker nucleophile or so on and so forth. Third thing we looked at was the leaving group. A better leaving group, a good leaving group, or a better leaving group is a weak base. And the better the leaving group is, the faster is the SN2 reaction because it leaves faster, so something else can come in faster. And finally, the fourth thing we briefly talked about is the solvent. Solvent, and the kind of solvent that SN2s like to use is a polar aprotic solvent compared to. Now, I have to say this because I don't want this to be a point of confusion for anybody. Solvent does not stop an SN2 reaction. Let's say, you might come across this, guys, using methanol for SN2. It doesn't mean that that SN2 won't happen. It will happen. It just might be slower. That's all it means. Yes,
So between the 4 groups, is it in order with which was more important?
we go in this order.
Okay.
We should always look at this first. If that's the same, then we look at this. If those are the same, then we go down there. And of course. So we have to look at them in the order. Sounds okay, everybody? Okay, before you leave, please take this worksheet. I really need you guys to start doing, and I think I've posted this on Canvas, I'm not sure. I need you guys to be working on these on your own. The keys are provided because we have limited time, guys. We don't have unlimited time. So, work through, I'll tell you which page in just 1 second. I think we can do page 1. I think we can do page 2. We can do page 3. We can do page 4. We can do page 4, but maybe the last mechanism on page 4 is where we will start with on Monday. Okay? So maybe that's the one we will do on Monday together.
Don't we have a holiday?
Oh, did I say Monday? Yes, you're right. We do have a holiday. Thank you. Wednesday.
Okay, now, for the lab, any suggestions or changes?
What are we doing? Oh, no. It's pretty straightforward. Yeah, the
Same
book is
one.
good.
Okay.
Yeah,
Is it-
yeah, same one. Because I changed it. No, have you seen the new schedule?
Yeah, you just changed one, right?
No, but then I moved everything down.
Yeah. uh-huh.
Yeah, absolutely.
Okay.
Yeah,
So it's the same order, it's just we take one out and we move.
and then everything moves down.
Okay.
But I posted the new. So
Yeah,
yes.
I actually printed it. It's
Oh,
not this one.
perfect.
This is the old one.
Okay,
But
good.
I printed it the new one. But so we have N-butyl bromide.
No.
No.
See, we pushed all of these down. So now we are doing this. Here.
Oh, so now we are doing these
See,
ones.
we took this.
Yeah, I got you.
And put it in,
I got
and
it.
then
Okay. I thought we just
Reactivities of some alkyl halides.
Oh, okay.
Did
Oh, well, it is this one, yeah. It is.
On a place over here, like the major.
Not both. Not both. That's why I asked you which one.
Oh.
That's benzylic, that's just tertiary. They're both tertiary, I get it. That's why you probably circled both of them. Or you said both.
No, I said only one. But the green one is.
No, you had that.
No, I.
No, you had. No, you had.